Assalamualaikum. Welcome back to Cirque Labs Physics and Chemistry tutorial for high school students. In today's episode, we look at two problem applications of Dalton's law of partial pressures. How do we compute the total pressure of a mixture of gases given its volume, temperature, and the number of moles of each gaseous substance? Find out. Stick around, watch and learn. The questions are: number 1, a 5.73-liter flask at 25 degrees Celsius contains 0.0388 mole of nitrogen gas, 0.147 mole of carbon monoxide, and 0.0803 moles of hydrogen gas. What is the total pressure in the flask in atmospheres? Question number 2. What is the pressure of a mixture of 0.200 grams of hydrogen gas, 1.00 grams of nitrogen gas, and 0.820 grams of argon gas in a container with a volume of 2.00 liters at 20 degrees Celsius? Before we answer these questions, let us look at Dalton's law of partial pressures. It says that the total pressure of a mixture of ideal gases is equal to the sum of the partial pressures of the component gases. In formula form, the total pressure is equal to the sum of the partial pressures of, for example, gases A, B, and C. In this formula, P total refers to the total pressure of a mixture. P sub A, P sub B, and P sub C are the partial pressures of gases A, B, and C, respectively. If equal volume cylinders containing gases at pressures 300 kilopascal, 600 kilopascal, and 450 kilopascal are all combined in the same size cylinder, the total pressure of the gas mixture is 1,350 kilopascal. Moving on now to question number 1, we are asked to find the total pressure of the mixture of three gases in a flask of fixed volume and temperature. So we just use the ideal gas law equation, P equals nRT over V. The first gas is nitrogen gas. Its number of moles is 3.88 times 10 to the negative 2 moles. All right, so we multiply that by the universal gas constant, big R, equal to 0.08206 liters atmosphere per mole per Kelvin, and then multiply that also by the absolute temperature of 298 Kelvin. All right, that's the equivalent of 25 degrees Celsius given in the problem. Then the product is to be divided by the given volume of 5.73 liters. So doing our math, we find the partial pressure of the nitrogen gas equal to 0.166 atmospheres. Computing the partial pressure of carbon monoxide gas, we follow the same formula. The given number of moles for carbon monoxide, which is 1.47 times 10 to the negative 1 mole, all right, is also multiplied by the same constant, capital R, and also by the same absolute temperature, 298 Kelvin, and their products to be divided by the same volume, 5.73 liters. So again, doing our math, we get the partial pressure for carbon monoxide gas equal to 0.627 atmospheres. And similarly, for the partial pressure of the hydrogen gas, whose number of mole is 8.03 raised to the negative 2 power, all right? That's in mole. Again, multiplying that by the constant, big R, and the same absolute temperature, and then divided by the same volume, we get the partial pressure for the hydrogen gas equal to 0.343 atmospheres. And adding them all right, the partial pressures such as 0.166 atmosphere plus 0.627 atmosphere and 0.343 atmosphere, we get the total pressure of the gas mixtures, which is equal to 1.14 atmospheres in 3 significant figures. For question number 2, we are given the masses in grams of hydrogen, nitrogen, and argon gases in a mixture of 2.00 liter and temperature of 20 degrees Celsius or 293 Kelvin. So just like in question number 1, we are also asked to find the total pressure of these gases. But since what we are given here in question number 2 are the masses in grams of the gases, we need to find their mole equivalents. Okay. For hydrogen or hydrogen gas, all right, we just divide the given mass of 0.200 grams by the given molar mass of hydrogen, all right, which is 2.00 grams per mole. So that will give us the mole equivalent equal to 0.100 mole. Now for the nitrogen gas, okay, there's 1.00 gram of nitrogen gas given. So again, dividing that by the molar mass of nitrogen, 28.0 grams per mole, we also get the mole equivalent for the nitrogen gas equal to 3.57 raised to the negative 2 power mole. And lastly, for the argon gas, whose given mass is 0.820 grams, dividing that by the molar mass of argon, or actually the atomic mass of argon, equal to 40.0 grams per mole, so we get its mole equivalent equal to 2.05 raised to the negative 2 power mole. Right? So, before we can find the total pressure of the mixture, there is a need for us to determine the partial pressures of each of these gases, again using the ideal gas law equation, starting with hydrogen gas. All right? So the computed number of mole, 0.100 mole, again is multiplied by the gas constant, 0.08206 liter atmosphere per mole per Kelvin, times, all right, the absolute temperature of 293 Kelvin, which is originally 20 degrees Celsius, and then divided by the given volume of 2.00 liter. So doing our math, we get the partial pressure for the hydrogen gas equal to 1.20 atmospheres. For the nitrogen gas, its number of moles, 3.57, all right, times 10 to the negative 2 power, that's in mole, again multiplied by the value of the big R, or the gas constant, and also multiplied by the absolute temperature, 293 Kelvin, and the product to be divided by the given volume, 2.00 liter. All right? So doing our math, we get the partial pressure of nitrogen gas equal to 0.429 atmospheres. Likewise, for the argon gas, its mole equivalent is 2.05 raised to the negative 2. So multiply that by the value of the big R and the absolute temperature, the same absolute temperature, 293 Kelvin, and to be divided by the same volume, 2.00 liter, we get the partial pressure for argon gas equal to 0.246 atmospheres. Hence, we can now determine the total pressure of the gas mixture. So we just add the individual partial pressures, 1.20 plus 0.429 plus 0.246 atmospheres, and we will get the total pressure of the mixture equal to 1.88 atmospheres, rounded to 3 significant figures. So that concludes my lecture. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.